Welcome to our discussion on formal arguments. In this section, we'll be talking about operator scope and logical equivalence. This is part 3. So where we left off is that we discussed the way that simple thoughts come together to make complex premises. And the way that they do that is by a function that we label as operators. And we identified 5 different operators, which are conjunction, disjunction, conditional, biconditional, and negation. The previous video went into detail on each of these, but in short, depending on which operator the compound uses, we can determine the truth value of the compound based on the truth value of the components. The scope of an operator is how much the operator applies to. In the examples we've been looking at, there have only been 2 components, or 1 in the case of negation. In these cases, it's clear which components the operator applies to. And operators will continue to apply to only 2 components, no more, except for negation, that applies to 1 again. But you must remember that we are looking at the form of an argument, not actual premises when we look at the truth tables and how the operators, operate. And while we've been using simple sentences for examples, these variables can actually be made up of other well-formed premises, which can themselves be expressed via operators. So, for example, a negation could be one of the conjuncts in a conjunction. The scope really becomes apparent when you begin to think about complex sentences. Many may have more than one negation or conjunction present, so the operator's scope will indicate which components to which it applies. If we don't indicate the scope, we have ambiguity. It becomes difficult or perhaps impossible to make sense of all the variables and symbols. So when we use our shorthand system, we indicate scope with parentheses. If the component is that of a larger compound, the parentheses indicate where the application of the operator ceases. You might conversely think of this as saying that if there is a parentheses, the contents of the parentheses are part of the larger compound. The parentheses act as that variable. They form the bounds, as it were. Any complex compound premise will have one operator that has the largest scope, which itself is not enclosed in parentheses. This is known as the main operator. So here's an example. If the ground is saturated with water and a big rain occurs, then there will be a flood. Using that premise, let's draw out the simple sentences. Let's have G mean the ground is saturated with water, R is a big rain occurs, and F to be there will be a flood. Now I want you to think about how those simple sentences interact with each other, with operators. You will notice that there is both a conditional, an if-then, and a conjunction present in the original premise. And if we evaluate it further and kind of zoom out, we can see that the main operator is the conditional because the entire statement is a big if-then statement. The conjunction serves as the antecedent to the entire conditional, being if the ground is saturated with water and a big rain occurs. That's the first part of the larger sentence. We would express this as such: open parentheses, G and R, close parentheses, arrow, F. It's kind of difficult to read that out loud, by the way. So, to explain the example, I want you to notice that this is really nothing new. The rules for conjunctions and conditionals still apply. This is still a conditional statement, and it fits the same the truth table. The only concept added is that the antecedent, right, the GR, has its own truth table now when we would need to consult to establish the truth of the conjunction. We would need to establish the truth of this conjunction before we could move to establish the truth of the conditional as a whole. Okay, so maybe this will be a little easier to see. Let's take the cliche, you can't have your cake and eat it too, and break it down. If we have the most basic components, C equals you can have your cake, and T equals you can eat your cake, we can express that as a negation of the conditional of the two, right? It's not the case that you can have your cake and you can eat your cake. In this case, the negation is the main operator and the conjunction is its subordinate clause. This might sound a little weird, the whole it is not the case that you can have your cake and eat your cake, but that's in part because there are multiple ways of saying this concept. For example, if you eat your cake, then you can't have it. Or either you can have your cake or you can eat your cake, but not both. Both of these alternative versions are logically equivalent to the original. What? So, what is logical equivalence? As my brilliant transition suggested, logical equivalence is when two things, said in a different way, are actually the same. This is by virtue of the operator functions interacting with each other. You've probably encountered this if you've ever gotten to a verbal fight with a friend, or perhaps a loved one, or an argument, and you go at it for a while, only to realize in the end you're ultimately both saying the same thing. But usually there was some kind of misunderstanding or some kind of different use of words that prevented you from really hearing each other. Consider this for a teaser, because we're going to get into the rules of logical equivalence. There are certain rules that govern this feature. How about transposition, which says that the antecedent and consequent of a conditional can be transposed or flipped if you negate each. Now that sounds kind of kind of weird using the terms we've been just recently introduced to, but it's going to be very intuitive. Take the example, if it's raining, the ground will be wet. That's the same thing as saying, if the ground is not wet, then it is not raining. This is the rule of transposition. It's a form, again, that says, given a conditional, we can do this, and we will have the same truth value. You can see how it's expressed here. If R, then W is equivalent to if not W, then not R. Notice that negation does not need the parentheses around the R to indicate its scope. Negation is the only one that has one variable, so you won't need to do that. However, you'll remember that the previous example did have a negation on the outside of a parentheses. That just indicates that it is the primary operator and that the conditional is its variable. The concept of equivalence might seem trivial on the surface, but remember, we are working with a system, and it's important that within a system we set out the rules and we see what we can apply to get an outcome and how we can manipulate form and change it to a different form so that we can plug it in. And really, it will become more apparent once we get into showing the rules of inference and into the proofs of logic. And perhaps it'll be a bit more intuitive once we discuss the actual rules of equivalence in our next video. Thank you for watching. I'll see you next time.